Now we're going to fill out our number circle for ones complement. So ones complement, right, we still have our leftmost bit is our sign bit, but then if we want to invert the sign, right, go from negative to positive or positive to negative, we just flip all of the bits. And we never let the magnitude go into the most significant bit, because otherwise that would kind of break our system. So once again, we are in this case where we're kind of divided here, where we're going to still have our positive numbers here and our negative numbers here. And so we know that if we're positive, we can just read the magnitude as normal, right? If we're positive, we can just read the magnitude as normal. So that means this right side is all just kind of like regular unsigned. 1, 2, 3, 4, 5, 6, 7. All right. Now, what do we have here? Well, we've got 1, 0, 0, 0. So this is a negative number, and so to get the magnitude in our heads, we can take all these ones and flip them, so that makes it 1, 1, 1. And so that's telling us what the magnitude is, and 1, 1, 1 is 7. So we've got negative 7 here, right? This is negative 7. All right. Now, let's try this one here. So we know it's negative, and then we look at these 3 bits here. And what do these 3 bits tell us? Well, if we flip them, we get 1, 1, 0. And so that's 6. So that means that this is a negative 6. And we're going to assume that the pattern actually, now we've got 2 of them, we can assume the pattern kind of flows through the rest here. So negative 5, negative 4, negative 3, negative 2, negative 1. And what about here? Well, we know it's a negative, but we've got 1, 1, 1. So we flip those, that's 0, 0, 0, which is a 0. So we've kind of got a negative 0 situation going on here. So now let's look at our properties and see if we've got what we want. So the first thing is a single 0. Do we have a single 0? Well, no, we've got 2 here. We got 1 here and 1 there. So that's a no. Do we have a clean 0? I would say, we do have a clean 0, but we also have a very unclean 0. And if we have an unclean 0, then that means the whole thing, I would say, is no. Unidirectional increase. Well, let's test this out. 0, 1, 2, 3, 4, 5, 6, 7. And then we drop to negative 7. And then negative 6. So we are increasing. We could say that our max is here and our minimum is here. And we bounce around. And then here we've got this hiccup where we go from 0 and then another 0, right? So it's kind of like this. As we increase, as we go around, it might be something like, and there's a little spot where it doesn't change as we count. And so just because of this hiccup, quote unquote hiccup, that I actually tend to disagree with fellow academics. They'll say that this actually is unidirectionally increasing. As we go around, right, if we start at our minimum and we count around, it is increasing, and it's always kind of by 1 unit, besides for this hiccup. And they say we don't have to worry about the hiccup. It's still unidirectional increase. I say that hiccup is significant, and so I will say that it is not a unidirectional increase. Some other people may say it is, but by my logic and by the way I interpret the definition, this is not a unidirectional increase. So just if you ever get asked this question, make an argument for whatever you think is right. You know. Uh, anyway, clean rollover. Well, do we have a clean rollover? That's asking, is our max next to our minimum? And in this case, yes, it is. Right, our max is right here, and our minimum's right there. So yes, we do have a clean rollover. And do we have a full range of values? Well, we don't, because we have two zeros here, right? And this zero sequence, one of these zero sequences could be used to represent a new number rather than representing 0 twice. So we do not have a full range of values. So once complement is a little useful, I mean, it's got one property, arguably two properties that we want, but it doesn't quite have all of the properties that we would want.